Section 1.2, Operations on Functions. Our objectives are 1. Understand composition of functions and notation in tables, graphs, and as formulas. 2. Construct new equations from our basic toolkit functions using transformations, including A. Vertical and horizontal shift, B. Vertical and horizontal reflections, C. Vertical stretch or compression, and D. Combining transformations. Composition of functions is a key technique we will use throughout the course. Transformations give us an important tool for expressing a variety of types of relationships. Composition of functions is when the output of one function is the input of another. We can write it f of g of x. That's the same thing as f compose g of x. Note that we work from the inside out, so we would evaluate g of x, and then that output would become the input of f of x, no matter which way we write it. Note that that implies that the range of g, the inside function, has got to be the same as the domain of the outside function. Composition of functions using graphs. Let's let the graph on the left represent f of x and the graph on the right represent g of x. We can evaluate at particular points using the graphs. For example, g of f of 1 means we evaluate the function f at 1 and take that output and use it as the input of g. So first we want to find what is f of 1. We go to the input. F of 1 is 1. So g of f of 1 would be g of 1. G of 1, here on g we find 1. That's negative 1. Similarly, we could evaluate f of g of 4. So g of 4, g 1, 2, 3, 4, 1, 2, 3, 4, 5. So g of 4 is negative 5. So f of g of 4 would be f of negative 5. So now we have our input. We go to negative 5. What is f of negative 5? And it looks like that is 1. Composition of functions using tables. We use the same logic as we just used for graphs. You would find the output of the inside function and use it for the input of the outside function. Composition using formulas. Input values of functions can be constants, variables, or algebraic expressions. Composite functions are a way to express this. For example, let f of x be x squared minus 3 and g of x be the square root of the quantity x plus 2. Then f of g of x would be, we take all of g of x and input it for the x. So f of g of x would be the quantity square root of x plus 2 squared minus 3. Similarly, g compose f of x. Remember that's g of f of x. We would take all of f of x and use it for the x in g of x. So that would be the square root of, wherever the x is, we put in all of f of x, x squared minus 3, plus 2. Let's look at some applications of composite functions. Suppose r of p is 2/10 p plus the square root of p is a tax revenue as a function of the population in thousands, and p of t, 75 plus 3t plus half t squared, where t is years after 2015. Find a formula for tax revenue as a function of the year. So the input in the revenue function is the population, but the population is a function of the year since 2015. So if I insert all of p of t for p, what I'm doing is r of p of t, which would be the same as r compose p of t. So everywhere there's a p, we fill in the entire function p of t. And we now have revenue as a function of t years after 2015. We can also write a function as a composition of functions, and this will become an important perspective later on in the course. There's more than one way that you could break a function into composition of functions. I'm just going to choose one. So I notice that f of x is a polynomial to the third power. So I'm going to let g of x be x cubed and h of x be x to the fourth minus 7x plus 3. Then g of h of x is f of x. Similarly, I can see here I'm taking a polynomial to the square root, so I can say let g of x be 5 plus the square root of x, and let h of x be x squared minus 7. Then g of h of x, that is g compose h of x, is f of x. Let's move on to look at transformations of functions. Transformations let us construct new equations from our basic toolkit functions. Vertical shift. Given a function f of x and another function g of x equals f of x plus c, where c is a constant, g of x is a vertical shift of f of x by c units. If that constant is a positive number, it's going to move the original function up. If that constant is a negative number, it's going to move that function down. Horizontal shift. Given a function f of x and g of x equals f of the quantity x plus k, where k is some constant, g of x is a horizontal shift of f of x by k units. For a positive k, the whole function is going to move to the left. For a negative k, the whole function is going to move to the right. This may be counterintuitive, but when you experiment, you'll see that that is what happens, and you'll understand a little bit better why. Let's work an example. Consider what you expect, and then sketch a graph of f of x equals the quantity x minus 3 squared minus 2. First of all, I recognize that this function is a variation on our basic toolkit graph. I'm going to call it g of x now, equals x squared, which looks something like this. And I can see by looking at this function that the negative 2 is a vertical shift down 2, and the negative 3 is a horizontal shift 3 to the right. So f of x, I'm going to orient on the vertex here. I expect the vertex to move from 0, 0 to down 2, 3 right. So I expect my graph to look something like this, with a vertex here, now let's go ahead and graph on our calculators and see if we're right. So we're going to go to the y equals, clear out whatever's there, x minus 3, quantity squared, minus 2, graph. And it looks darn close to my graph here. And if I blow it up a little bit, like say look at zoom standard, it looks even more like what I just drew. Let's talk about reflections. Vertical reflection. G of x equals negative f of x is a vertical reflection of f of x about the x-axis. So that means we expect it to be reflected around the x-axis. Horizontal reflection. H of x equals f of negative x is a horizontal reflection about f of x, about the y-axis. So we expect this to reflect this way. Let's consider what we expect and then sketch a graph of f of x equals negative x squared and h of x equals negative x cubed. So I can see that this f of x is a vertical reflection of our toolkit function. So I expect it will look something like this. H of x equals negative x cubed, I recognize is a transformation of the toolkit function x cubed which looks something like this. So I expect h of x to be reflected in the y-axis to look something like this. So let's confirm with our graphs. Negative x squared. Yep, looks just like we thought it would. Negative x to the third power. Looks like we thought. Let's look at the above and identify the intervals where the function is increasing and decreasing. So we're just going to focus on a couple of these. Let's look at f of x equals negative x squared. For this function, I can see that f of x is increasing all the way until I get to 0, and then it's decreasing every value after that. And at 0, it is neither increasing nor decreasing. So for f of x, as x, let's see how I want to write this. We're going to use interval notation. F of x is increasing on the interval from negative infinity to 0, not including 0, and it is decreasing on the interval from 0 to infinity, not including 0. What's happening at the point 0? At the point 0, f of x is neither increasing nor decreasing. Okay, how about our h of x? In our h of x, as x gets larger, f of h of x gets smaller and smaller and smaller. So h of x is decreasing from negative infinity to infinity. That is, for all real numbers. Now we're going to take a look at vertical stretch compression. Suppose g of x is some constant times a function f of x. So k is a constant. This is a vertical stretch or compression of the function f of x. If k is greater than 1, the graph will be stretched. If k is between 0 and 1, then the graph will be compressed. If k is negative, there will be a combination of vertical stretch or compression with a vertical reflection. When we're graphing a combination of factors here, so I've got A is our compression or stretch factor, K is our horizontal shift, C is our vertical shift. If you're graphing something like this, you want to first consider your stretch or compression and then take into account your shift vertically and horizontally. Let's look at f of x equals x squared, f of x equals 2x squared minus 3, and f of x equals 1/2 x minus 2 quantity squared plus 4. So we know our basic shape f of x already. What do we think is going on here? I can see that I have a vertical stretch occurring because my constant, the coefficient on the squared term, is greater than 1. I can also see that I have a vertical shift down. So let's compare x squared to 2x squared to get an idea of what's going on with this stretch. If I first put in x squared, we know what that looks like. Then we put in 2x squared. Look how it changes. It looks like it's getting skinnier. And the reason it's getting skinnier is this is stretching up. So, for example, if we just look at a few tables, we can get an idea. At 1, x squared is 1. At 2, x squared is 4. At 3, x squared is 9. At 1, 2x squared is 2. At 2, 2x squared is 8. At 3, 2x squared is 18. So where we're achieving these points is much higher. That's what we mean by a stretch. So when we look at this graph here, 2x squared minus 3, we expect that stretch. So it's going to be skinnier because we're attaining the higher points faster, and we're going to move down 3. So I expect this will look something like let's see. From 1, I would hit 2. So over 1, I would be 2 up. Over 2, I would be 8 up. 1, 2, 3, 4, 5, 6, 7, 8. So f of x equals 2x squared minus 3 looks something like this. What about f of x equals 1/2 x minus 2 quantity squared plus 4? I know that this is a vertical shift up 4. I know that this is a horizontal shift 2 to the right. What's going to happen with this compression factor? I know it's a compression factor because this constant is between 0 and 1. If we want to look at it by points, at 1, I'm only going to be at 1/2. At 2, we're going to be at 2. At 3, we would be at 4.5. So you can see that we're attaining our height a lot more slowly. That's what we mean by compression. So what I would expect this to look like is my vertex would be at, let me make room. My vertex would be at the point 2, 4. And if I go 1 to the left, I'm only going to go up 1/2. If I go 2 to the left, I'm going to go up 2. So I'm expecting it to look something like this. Let's take a look at the compression on our calculator. So I'm going to go ahead and leave the x squared there so you can see how the change in the coefficient, our stretch compress factor, changes the graph first, and then we'll go ahead and put in the horizontal and vertical translations. So if I put in a half x squared, you can see that the graph is a lot fatter. It's outside. This is the original f of x is x squared. Let's go ahead and put in our horizontal and vertical translation factors into our new equation. Might want to notice, if you didn't know this already, if I hit second delete, that means insert, then I can enter characters in without deleting what's there. So that can be a handy way to change what you're doing. Whoops, got my squared in the wrong place there. So here's my original, and here's my new graph, and notice how much wider it appears.